Hello friends, in today's class we are going to talk about another deadlock avoidance algorithm called Banker's algorithm. So welcome here and we are talking about Banker's algorithm, and we have already seen a graph method for the avoidance, and that only works if graph contains cycle and it is only applicable for a single instance. Okay, single instance, so that is we can conclude directly that if a graph contain and single instance of the resource is there, then we can directly conclude that that there is a deadlock. So it does not work with multiple instance, and for that we need another algorithm, that is a Banker's algorithm. It works with multiple instance, and each process must priori claim maximum use. So process has to say that if the resource type is R1, I need maximum four instance of it. When a process requests a resource, it may have to wait. Okay, so immediately it will not be assigned the resource. When the process gets all its resources, it must return them in a finite amount of the time. So no infinitely blocking of the resource. If you have done, then please return it. Now these are the some data these are the some values that data that we are going to use, and few vectors are there. In this case, let n is the number of process. Okay, now small n is the number of process and m is the number of resource type. Okay, so suppose there are p1, p2, p3 is the process, and r1 and r2 is the resource type, two resource type, then m value is equal to 2 here and n value is equal to 3 here. Available vector of length m, if available j is equal to k. Okay, vector of length m, available j is equal to, then k instance of resource type rj is available. Okay, so suppose r vector length m is equal to 2, and suppose 4, and if I say 6, so that vector 4 6 describe that there is a 4 instance of resource type r1 is available and 6 instance of resource type r2 is available. Max is an n cross m matrix. Like here it will be 3 cross 2 matrix. 3 is the process, 2 is the need, where max I j is equal to k, then process pi may request at most k instance of resource type rj. Process pi may request at most k instance of resource type rj. So suppose I draw this matrix for you. In this, suppose this is p1, p2, p3, and this is my max matrix, and suppose this is your 4 2 1 3 and 2 2. That means resource type r1 maximum that p1 can claim is 4, and r2 maximum it can claim is 2. 1 3 for p2 process p2 and 2 2 for process p3. Allocation is another matrix of n cross m matrix, and here again we have, this is the maximum, and this is your allocated, means what is already been allocated to. Suppose 1 0 1 2 and 0 0 0, nothing has been allocated. P is currently, what is the definition? Pi is currently allocated with k instance of rj. Okay, k instance of rj. Okay, so this is your maximum requirement, and this is the allocation that has been done. Need matrix is something that need is n cross m matrix, and the requirement. So what is the requirement here? Maximum 4, allocated is allocated only 1. So the need matrix is maximum 4 and allocated is 1, and that is your 3 minus that 4 minus 1, that is 3. 2 minus 0 is 2. 1 minus 1 is 0, and 3 minus 2 is 1. 2 minus 0 is 2, and 2 minus 0 is 2. Okay, so that is your need matrix. Okay, and that will come as need of ij is equal to max of ij minus allocation of ij. Okay, so that is your need matrix. So available is that vector m is there, max, allocation and need are the vector of n cross m. This is the safety algorithm that we have here in this cases, and in safety algorithm, what we'll do here in this case is work and finish with the vector of length m and n. Okay, work, there is a work vector, and there is a finish vector. Okay, so work is equal to what? Available, and finish vector is for finish I, means here in this case is a work vector is for instance m, and finish vector is equal to your n number of process. So initially what we'll do, that if we have 3 process, then we'll say finish 0 is equal to false. I'll say finish 1 is equal to false, and I'll say finish 2 is equal to false. So none has been finishes till now. Okay, now here in this is find an instance I such that both, okay, finish I is equal to false. Here in this case is finish I is equal to false, and need I is less than equal to work. Okay, we find both of this. So I that it hasn't been finishes, and its need is less than equal to available. Okay, need I less than work is, need I is less than equal to work is less than your whatever available. Okay, if no such I exists, then we terminate it, and if all of them are true, then it is in safe state. But if all of them are false, then we cannot simply satisfied, and that is a difficult situation, and we can say deadlock. So what we'll do here, work available will become available plus allocation. Okay, what we'll do, we assume that we can satisfy the need. We can satisfy the need, and after using the resource, it will free the resource. So work will become work plus allocation. That means it will return the resource, and it will become finish I, it will become true. Okay, and then you can go to the step 2. Again you find out such. So if with the based on this work, based on this available, we will be keep on updating this work whatever been allocated. Suppose 4 is available, and for I available is 2. So after this I can satisfy the request here, and after that what will happen, that this will be added, and this will become 6. So it says that if finish I is true for all I, then system is in the safe state. So that's all for this discussion. Thank you.